Alright guys, we're back at it again, just a little review. So in this scenario we had 6 liters of pure nitrous oxide and 5 liters of fresh gas flow of pure oxygen flowing in here. Now like we discussed last time, washout equation. The washout equation was concerned with how much nitrous oxide was left in your breathing circuit after so much time. Your washed-in equation was concerned about how much of your oxygen is now in here, what percentage is now in here after so much time. And we discovered through our makeshift scenario here that there was 19% left of nitrous oxide after 2 minutes, right? So the wash-in, like we said, was concerned about oxygen, is simply 1 minus 19%, whatever, 0.188. So it's essentially 81%. Just wanted to do a washout equation first, just to show you that they're essentially, as you can tell from the equation, they're very similar. They're two sides of the same coin. So we're going to continue on with Dr. Dave's bonus question here. So we have a situation where our fresh gas flow is 4 liters, nitrous 2 liters of oxygen, 4 liters of SIVO, or sorry, 4% of SIVO. And he asks how much time before you reach 90% concentration in your breathing circuit, right? And with our wash-in equation here, we're going to figure out just that, and we have to solve for t because he's asking for time, right? So let's go ahead and figure out some of these values. Now he asks, well, let's go ahead and figure out k first, like we did last time. Our k, now we have 4 plus 2 liters plus 4% of the 6 liters. That equals 6240 milliliters, right? So k equals 6240 over 6,000 equals 1.04. Okay. Now he's asking, when do you reach 90%? So let's go ahead and set the equation up. All right. So 90.9 equals 90%. 1 minus E. All right, and we have our K value, 1.04, negative 1.04. We're solving for time because he's asking at what point in time will you reach 90%. Okay, so let's go ahead and do some, the basic algebra here. I'm going to subtract 1 from this side. There might be a quicker way, but this was how I did it. And when you subtract 1 from both sides, you get negative 0.1 equals negative E to the negative 1.4 time. Now, whenever you have a variable in the exponent area, I completely forgot about this from my algebra classes 15 years ago, but to solve for a variable in the exponent, you have to take the natural log of both sides. So you're going to take the natural log of 0.1 equals the natural log of E. And then when you take the natural log of this base here, you can just drop all this down like it's just a regular multiplication problem, right? So it's negative 1.04 t. All right, so where did my calculator go? All right, so we're going to take the natural log of 0.1. Oh, you know what? I skipped a step here. Since we have a negative on both sides, you can just cross them both out. Or you can, in your head, move this whole equation over here and this whole equation over here, and you get positives on both sides. So I just skipped a step. So it's positive 0.1 and positive E. So I skipped a step there. But the natural log of 0.1 equals negative 2.3 equals, and natural log of E is just 1, right? So we have negative 1.04 t. All right. Now to solve this equation, of course, I think it's pretty simple. From here, you just take your negative 2.3, negative 2.3, divided by negative 1.04. All right, and you get your t equals 2.21 minutes. Now, how do we know it's minutes? How do we know it's not hours? It's because we're dealing with minutes up here, 6,240 milliliters per minute, right? So that is your answer. I hope this video helped you out a little bit in understanding.